Three, two. Hello, hello. Welcome back, everybody. Welcome back to the Moonwell competitive audit on CodeHawks. I'm here joined with Elliot, a dev from the team. Excited to have you here, Elliot. How are you today?
I am doing pretty well. How are you doing, Patrick?
I'm doing well. So, as a lot of the people who are watching this right now know, we took a brief peruse through the code base this morning where we built it. We worked with Slither. We ran it on Certora. And now we're really excited to kind of sync with you, get a better understanding of the code base at a high level from you. Um, and yeah, what's going on with this change? Because as our security researchers know, the first step to any successful engagement is going to be getting context. What is it supposed to be doing? What is the code supposed to look like? We have obviously most stuff in the README, but I believe we're going to walk through what you have, walk through the README, and maybe walk through some code and get an understanding of what you're concerned about and what you're nervous about. So,
Yeah, so for some context at a really, really high level, um, this this these changes are meant to um, fix some issues there were around bad debt created by the Nomad hack. Um, so when Nomad was hacked, it instantly made like all the you know, .mad tokens, USDC, ETH, and BTC, their version of those bridge tokens essentially worth zero. And these were collateral in Moonwell. So it was a really unfortunate situation. Um, I spent a, and kind of as, then we kind of spent some time thinking about how can we fix the situation and how can we restore liquidity to the markets by utilizing the Nomad collateral? Because essentially, there's when we started this project, there was about $3 million worth of collateral, of Nomad collateral, and there was approximately $8 million of bad debt. Now that number has changed. I think there's probably more than $3 million now worth of collateral, just as prices have appreciated. But still, I don't think it's enough to incentivize, or it's nowhere near being, fully collateralized. So it's not enough to incentivize anyone to repay their debts. Um, and so this is like a deferred, like slow motion liquidation. Because first, what has to happen is we need to zero out the borrow balances. And I guess let's start with like from a really high level. It took me a lot of time to figure out actually what the right thing to do was in this situation. So we have all these users who have a borrow balance, who have borrowed tokens but are never going to repay. So at first I said, okay, well, um, clearly because that amount is on the total borrows and it just keeps on accruing interest, that they're never going to pay back, right? Because if you have bad debt, why would you pay anything back? Um, so I said, okay, well, clearly the idea is the best thing to do would be to just subtract the bad borrows off of the total borrows, and then just leave things at that. But the problem is that actually violates key invariants of the Moonwell protocol. Um, and so I had to kind of go deeper and think about, okay, well, actually, what is the right thing? And so one of the invariants that violates is that total borrows is equal to the sum of all user borrow balance current. So we want to know that like the total borrows is equal to the sum of all these user balances. And if we just subtract off of the total borrows the amount of bad debt, then it won't accrue interest on those further, you know, bad debt amounts. But then if any user repays in the future, it actually breaks that invariant, and then maybe some users actually, can't fully repay off their debt because it would put the total borrows, um, it would subtract, it would be more greater than the total borrows. So like that wouldn't be a correct solution. So we went one step deeper and we said, okay, well, um, yeah, we need to make sure that as we're liquidating these users slowly, we need to make sure that that we're getting the current borrow balance that they owe. So this was actually an issue that I caught in the code as we were writing it. Yeah, is that we need to get the current borrow balance and subtract off of that, off of the total borrows. And then, so we have two different M tokens that we care about. And so Moonwell was forked off of Compound. So when we say M tokens, that corresponds to a C token in the original Compound version. So we have two different types of M tokens. We have the mfrax M token, and we have the xc dot M token. And both of these tokens are going to be upgraded to let me close this out, to the delegate fixer. So this is a contract that is only, I think, 68 lines of code or 62 lines of code. And so we have two main types of methods. The first type of method is one that we can, and you'll notice the safe math in here because this is an older Solidity version. We didn't want to change anything about the Solidity version because that would it would require changing logic, and then it would require us to re-audit the whole MERC20 delegate contract, which we did not want to do. So there's two kinds of methods in this fixer contract. The first is to repay bad debts. So we added a new variable here, and as you can see in the README,
Could you actually zoom in a couple clicks? Yeah, better. Good.
better. Okay, cool. So as we can see in the README, we have storage offset verification. So we really tried to do our homework before we came for this audit. So to me, I think there's probably like between 5 and 7 types of testing that make sense to run before you want to hand your code over to an external security reviewer or team. So that would be unit testing, integration testing, fuzz testing, invariant testing, formal verification, static analysis, and symbolic execution. And so for this project, unit testing didn't really make any sense because there were so few branches and so few lines of code, and we could test all of the branches post governance proposal. But we did use Slither to do like static analysis and make sure we didn't like introduce any new bugs there. We used formal verification to ensure that key invariance around the share price and that relationships between variables always held. And we did add some fuzzing to the integration tests. So, and we did also 4 or 5 internal code reviews. Well, probably 3 internal code reviews. We brought in 1 external like DeFi engineer who was who actually created the system originally. And then we also brought in an external security researcher who has been doing smart contracts and blockchain security for the past 4+ years. So I feel very confident in this code base, but let's go ahead and dive into the storage offset verification. So we want to do a diff of the storage offsets of the old token versus the newly upgraded token. So we can go ahead and run this command here. Okay, let me go ahead and make this bigger here. Okay.
For those who can't see, he's running the Slither command on the MERC20 delegator fixer with the -- print variable order.
Yeah, this is a very handy flag here. Slither allows you to print out the variable order, and yeah, no, it's just very nice for these kinds of things where you want to make sure that as you upgrade a contract, you're not breaking any storage. Um,
I think Forge has something like that too. You can do like Forge, inspect contract name storage. Um,
hmm.
that one's pretty cool too.
Yeah, I think they do a similar thing where they'll show offsets of their variable names.
Yep.
Yeah. Um, okay, so we'll let that run in the background, but from a high level now, we know what we're trying to do. We added a new, so let's I guess let's go down to the um, because even though these are like it's a really small change, it's kind of open heart surgery on the contracts, and it took a while to even reason about what needs to happen. Um, so in the compound white paper, the exchange rate is defined as the cash, which is the sum of the underlying token balance of the M token plus the total borrows minus the reserves divided by the total supply. So that's the exchange rate. Now, what we're about to do, if we hop over to this contract, we have the bad debt variable, um, and we have our main method that allows us to liquidate users. We have a fixed user function. So without getting too into the weeds here, every time we fix a user, we're going to take the amount of borrowed assets that they have currently, according to the current borrow index, after interest is accrued, and we're going to add that onto the bad debt. But as we add that onto the bad debt, we're also going to subtract it off the total borrows. Um, and so there's some questions here, right? Like, is the share price going to remain intact? Or like, how do we make sure that the share price stays the same? Because if we did this fix um, and and applied these changes, and then um, it somehow changed the share price in a way that would favor users that were already had um, exited their position, or favored users that were first to to redeem their underlying assets or their M tokens, then that wouldn't be fair. And so we want to make sure that there's no possibility for MEV here, and that we're not going to change the share price at all. So this is the current exchange rate. It's cash plus total borrows minus reserves. We've just seen in our code how we're about to modify the total borrows, right? Every time we fix a user, we're going to subtract their debt off of the total borrows. And so but we also don't want the M token share price to change, because if we just subtracted the total borrows from here, it would cause the exchange rate on both affected M tokens, on the MFRAX and MXC dot, to reprice down in a pretty significant way. And we don't want to do that. So what we're going to do is we're going to add a new variable into the mix. This is the bad debt variable. And this variable is going to be added onto the cash and the borrows. And so now we can preserve our exchange rate, because we say, okay, our exchange rate is cash total borrows minus reserves divided by supply. But now we subtracted the bad debt off of the total borrows, so the share price should go down. But we went ahead and we added the bad debt onto this variable here, and that bad debt is now added onto cash. So we've actually changed our definition of cash to be underlying balance of the M token of the underlying asset. We have the underlying balance plus the bad debt, and that's our new cash variable. So that's now included in the share price. And so we also have a lot of formal specifications that I think prove pretty well that this share price does in fact remain intact.
And just to jump in real quick, we had a question: is bad debt the same for every user?
No, so each user has a different amount of bad debt. And in these JSON files, mxc.json and mfrax.json, we have all of the users um, that have bad debt. So feel free to look through those. But also because because these markets are constantly changing and constantly evolving, what we actually saw was that when the audit initially kicked off, there was a user that did not have any bad debt because they had actually repaid in the time since we have code frozen and then got into audit. So I think that anyone who's looking to submit bugs, that could be a potential medium maybe, if you figure out how to word that right and figure out the impact there. So it's just a little bit of alpha for you guys.
Some alpha. We love alpha.
Free alpha. Okay. So so we have the exchange rate here. And I guess it's also worth talking from a high level about the two different types of upgrades that are going to occur. So we have the mfrax M token. And, we have the mxc.m token. And then we have, and so these are markets that are going to remain healthy and are going to remain not impacted by this change. There actually will be some impact. So when we subtract this off of the total borrows, it's going to change the interest rate for these markets, because now the utilization is much lower, because as the bad debt is written off, there will be, as the bad debt's written off, there will be much less, much less total borrows, which means that utilization on the curve will fall. For the Frax market, it won't have much of an impact because the rate, it maxes out at 1% interest at the top of the curve. For MXC dot, I think the change will be more pronounced because it has a regular IR model. So yeah, so those are the main downstream effects and things that are going to change. So those are the two healthy markets. Those are not going to change. Now we have three unhealthy markets. We have Nomad USDC, Nomad BTC, and Nomad ETH. All three of these markets will be completely bricked and will not be operational post-proposal. So it's very important that people who, want to repay their bad debt, why you would repay your bad debt, I'm not sure. But you must repay your bad debt in order to get the underlying Nomad assets before this governance proposal goes through, because what will happen here is then we have a regular MERC20 delegate fixer. So this is for Frax and XC dot. And then we have an MERC20 delegate MAD fixer. And so this contract is only supposed to take care of the Nomad markets. And so what this is going to do is it's going to sweep all of the underlying balance of that market to a liquidator address to perform the liquidation. And if we go and go back to our share price formula, we know that exchange rate is equal to cash plus borrows minus reserves divided by total supply. But we're about to sweep all of the cash out of the market without adding a corresponding variable there. So essentially, these markets are bricked beyond any sort of help. And we have integration tests that show that essentially, if you try to do anything after this governance proposal in these markets, you cannot. So that is expected behavior. And by removing all this cash, it's going to totally change the share price but it actually doesn't matter because no one will be able to redeem their M tokens for the underlying assets after this proposal is passed. So yeah, I guess it's a good place to start. Patrick, are there any questions before we dive into the code here?
Nope, go for it.
Okay,
Just
so
yeah, go for it.
sweet.
And
So we
if
have,
you want to zoom in, sorry, I want to zoom in again, 1 or 2 clicks. And then yeah, everyone watching, feel free to ask questions. We'll pop them on screen.
sweet. So we have this MERC20 delegate map fixer. So we inherit the delegate contract, which is the logic contract for the M tokens. So we have an MERC20 delegator. So this is the proxy contract that delegate calls the delegate contract. And we have the delegate contract. So this version of the contract literally changes nothing about the MERC20 delegate contract except adding a new method, sweep all. It's external, callable only by the admin, which in this case is the time lock. We call transfer. We send all the total balance of this address to the sweeper address, and then we require success. So I've also taken a look at the Nomad ERC20 tokens, and all of their entire all of their tokens are like completely ERC20 compliant. So there's nothing weird about like it doesn't return a Boolean. So we don't have to use safe transfer. We can just assert that there was success, just require success, and that's fine. So there's really not much to this contract. Only the admin can call it, and then it just transfers the token to the sweeper address. There's no address zero checks, and that's intentional because we have a pretty robust integration test suite as well as a governance proposal. We have a whole governance proposal tool that we built internally to handle any sort of changes that governance might want to make. And I'll get into that a little bit later when we go over the gov proposal. But for now, what you need to know here is that this contract is going to be used when we upgrade all of the Nomad M tokens. So Nomad BTC, Nomad ETH, and Nomad USDC. They're all going to have their implementations upgraded. And then in the gov proposal, we'll call in here and sweep all the funds and send them to the Nomad reallocation multisig. Okay. So let's go on to the next contract. So this one's a bit more involved. So we have the MERC20 delegate fixer here. And it inherits MERC20 delegate. It adds a single variable, bad debt, and then it has multiple events. So one event for fixing the user, one for having the bad debt repaid, and another having the bad debt repaid with reserves. So yeah, I guess let's get into it. So I think it makes most sense to start off on the fix user function. So first we're going to check. So we have two different addresses here, the liquidator and the user. So as I was writing this contract, I realized that so the Certora prover, it's found interesting bugs in the past around token transfers not working and around liquidations failing. And I think in both of those cases, in the liquidations failing or essentially not holding key invariance, the issue was the message sender was the contract itself. In this context, we're not going to worry about that because there's no way for this contract to actually like call itself. There's no like multi-call or anything weird like that attached to the MERC20 delegator. But also, if we didn't have this check right here, that the liquidator is not equal to the user, as we're going to see later in this function, the Sartora, we would have to constrain the prover and tell the prover that the liquidator must not be the user. Otherwise, it would trigger an invariant violation. And there would be the possibility for an invariant to be broken if governance messed up here. So we don't want that to happen. So we add this check here. We first check that the message sender is the admin. So only the admin can call into this contract. We make sure that the liquidator is not equal to the user. We check that when we call accrue interest, the market is healthy, and there's nothing strange that's happened. Accrue interest returns a uint, with 0 being no error and non-zero being an error of some kind. So we call accrue interest, make sure everything is good there. Now that we've called accrue interest, we can call borrow balance stored. Borrow balance stored is going to fetch, it's going to fetch the current borrow balance of the user. And because we first updated the interest index by calling accrue interest, we now know that when we call borrow balance stored, we are getting the current user borrow balance if they were to repay all their debts, at this very second. And that's actually very key, because in a previous version of the code, we actually we looked at the user borrow balance and we said, oh, okay, the user borrow, we'll just get the current, we'll just get the borrow balance from the principal. But the problem is, let's say the user's interest index is from 6 months ago. There's a whole bunch of interest between 6 months ago and today that has not been accrued and not been factored into that user's borrow balance. And so that was a really good catch internally. And I think this is also just generally something to look for, because there's not a whole lot of code here, but try to think about, is there a way that we have put this system in an incorrect state? So are we setting the indexes to something that they shouldn't be? Or are we, making way for a user to somehow desynchronize important variables or bypass invariants or bypass certain checks?
Got another 2 more questions actually. Is the bad debt just used as a counter for how many times a particular user have bad debt, or will it contain the borrow amount which is not returned by the user?
So the bad debt is the sum of all borrow amounts by all users with bad debt. So, and we're at the bottom of this function, we'll look at exactly how that's calculated. But really, bad debt is just the borrow balance stored of every single fixed user has been called with, and the sum of that, right? Just the sum of all principal.
And then another question: how is it handled if the admin is the user with bad debt? Are there multiple admins? Is that not a thing that can happen because the admin is a contract somewhere or something?
So the admin is the Artemis time lock on Moonbeam. So this is just governance, and it does not have any borrow balance or any positions in Moonwell. So you can assume that the admin does not have any bad debt, will never have any bad debt, and will never, really have a position in the protocol unless someone donates them funds. Because you would have to pass a governance proposal where you would take out a loan and do all that stuff. And there's only a single admin.
Cool. Makes sense.
Yep. Okay, so we get the user current principal. We require the principal is not 0. And yeah, we make sure the principal is not 0. And then we set the principal for the user to 0. So we just zero out the user's borrow balance. And then we set their interest index to equal the current index. So if they enter the market again, if that same user for some reason is going to come back, then we traded them just like any other user repaying a debt or getting liquidated, and we updated their index to be correct. So then we get the liquidated amount. So let's say a user has bad debt, But then they also have some M tokens of this particular contract. If they have both bad debt and tokens, then we need to seize their tokens, right? Because it's not fair that you would have bad debt and we just zero out your borrow balance, but then let you keep the M tokens that you already have on that market. Because it's safe to say that if you're being liquidated here, your collateral is far less than the amount you've borrowed. So we need to make sure that that is in fact correct. Okay, so now we have liquidated, and we make sure that liquidated, if liquidated is not equal to 0, then what we're going to do is we're going to go ahead and we're going to add the liquidated amount to the liquidator balance for this contract. And then and then we're going to go ahead and zero out the user account tokens. So we just delete that, just zero that variable in storage. So yeah, pretty simple. And now here's where we ensure that there are no changes in the exchange rate of the system when we do any sort of action in the system. So now we take the user borrow balance, the principal, and we add it on to the bad debt. Now, I think that it's overkill to do safe math here, because in order for this to fail, it would require that principal plus bad debt is greater than uint 256 max, which is a very, very big number. So I don't think that's ever going to happen. I think that's totally a non-issue. But in the interest of being just as sure as possible that we're not missing anything, we're not doing anything incorrect, we'll go ahead and use safe math. And then for the total borrows, again, I think we are maintaining the invariant, unless someone can prove otherwise, that the total borrows is equal to the user borrows for the sum, user borrows current for the sum of all user borrows on that market. So I think we're maintaining that invariant, which means that the total borrows can never go below 0 and underflow. So I think we're fine there as well. So here we take the total borrows and we set it equal to the current total borrows plus the principal, or minus the principal, sorry. So we have the bad debt and we have the borrow balance, the total borrows. The bad debt is going to increase and the total borrows is going to decrease. And if we remember our share price formula here, because we're decreasing the total borrows, we have to add that number back onto the bad debt to make sure that everything works out as planned. So that's the fixed user function. Now we have the get cash prior function. So this get cash prior function usually just returns this. But now, because we have this new variable bad debt, we have to add that on. And I didn't use safe math here because it really should be impossible that the sum of these two numbers is greater than uint max. And so really we'll just say that is undefined behavior and leave it at that. But if you could theoretically get the balance of these two things greater than uint 256 max atomically when it was not there previously, then you could change the share price and cause the M token to reprice. But I'm not concerned about that because I don't see a way for that to happen. But if someone could prove that this is a valid state that could be accessed atomically post governance proposal in a way that would be permanent and break the protocol, I would love to see that. Okay. So any questions so far before we go to the next functions?
So we also don't have to actually if people are here. So if you're also strapped for time, we don't have to go through every single function as well. But
I
yeah,
think we
looks like
should. Yeah,
cool. Sounds good to me. Yeah,
yeah.
cool. No questions so far.
Okay, cool. So now that we know how we're going to increment the bad debt variable, so those are the fixed user function is the only function that can increase the bad debt. And actually, a core invariant of this change is that if you call fixed user, the bad debt must increase. Um, so yeah, so that is a really key invariant. Um, so we have now the function repay bad debt with cash. So it's non-reentrant. I can't see a way that reentrancy would do anything, would allow an attacker the ability to do anything malicious because we're talking to a token that's trusted, that doesn't make any external calls on transfer. So again, I'm not seeing how reentrancy could be an issue here, but I've just added that in to be 100% sure. Um, and sorry, let me just go get a tissue really quickly. I will be right back. Okay, so we have the repay bad debt with cash function, and all of these functions, these new functions, we want to make sure that they enforce this exchange rate so that even if you call them, it should not be able to change the exchange rate atomically, assuming you've already called accrue interest. So we have repay bad debt with cash. The user passes in an amount, and anyone can do this. That's kind of the beauty. It's permissionless, and it's open for anyone who wants to help reducing the bad debt. So we take the bad debt variable, we subtract amount off of it with a error message here telling us, hey, you tried to repay more bad debt than currently exists. And so we've tested this branch in our integration tests. We get the token, which is the underlying address of the token, and we then transfer the tokens from the user into this contract in this amount, and we require that it was successful. So for both tokens that this will happen for, XC dot and Frax, both of these contracts return true on a successful transfer from. So, non-standard ERC20 tokens, that's not a valid, or ERC777, that's not a valid finding here because we are only looking for, for Frax and XC dot. And then we emit an event that says the bad debt was repaid and in what amount. Okay. So now we have the repay bad debt with reserves. So this function is a little bit more fun. It's a little more spicy than the last one. So let's say the protocol has some reserves built up in the Frax or XC dot markets. And while governance could sweep those funds, those underlying funds to the DAO, the problem is that would not be, if we have bad debt and we're sweeping reserves, then there's still an issue in the market potentially that has not been fixed, and we need to first make sure that the depositors of the protocol are healthy and in a good state, and the market is all correct before taking reserves to operate the DAO. So we kick the function off by caching the bad debt and total reserves variable from storage. And this is going to save us some warm S loads throughout the rest of this function. We then make sure that the current bad debt and the current reserves are both non-zero. If either of them are zero, there's actually no state changes that can happen. So we just want to cut things short if there is in fact nothing that can be done here. Okay, so we have, that is annoying. Okay, so we first figure out the amount that we're going to subtract off of both the bad debt and the reserves. And that's really just the lesser of the two. So whichever is less, we'll subtract from both. That's the rule. So if the current bad debt is less than the current reserves, then we're just going to subtract current bad debt and from reserves. But if that is not true, so if the current bad debt is greater than or equal to the current reserves, then we're going to subtract reserves off of both numbers. So we do a safe math subtract here. So we say, okay, for bad debt, we're going to subtract, and let's say that the reserves were less than the bad debt. So then in this case, the subtract amount would be the reserves. So bad debt would decrement by reserve amount, and then reserves would decrement by reserves amount, which would mean that reserves would now be zero. And then what if we have a scenario where bad debt is less than the reserves? Then we would say subtract amount would be bad debt. So then line 64, bad debt is equal to 0 because we subtract bad debt from itself. And then total reserves, we just subtract off the bad debt amount from reserves. And then total reserves is just, total reserves previous minus bad debt equals total reserves current. And then we have this event here where we emit the new bad debt, the starting bad debt, the new reserves, and the starting reserves. And that's really it. There's no other changes to this system. And it's funny because it looks like a really small amount of code, and it took a really long time to actually reason through the correct thing to do in a complex situation like this, because you have suppliers, you have borrowers, you have users who are like not really involved with this market at all, but still have, anyways, users who don't put up any of this asset as collateral, but they've supplied the collateral asset. So now it's a question of, okay, well, so if you change the exchange rate, then it would be unfair to the current holders of the M token, and then the users who are borrowing would get a break when they don't really deserve it. So yeah, so it took a lot to reason through this. And then also there's a governance proposal that we can run through of exactly how we create the gov proposal, because there's around 50 actions there for that the DAO has to take. So I'll pause here. Are there any questions before I continue?
Looks like you're good.
Okay. Okay, so let's look at the gov proposal here. So first of all, this repository makes use of the forward proposal simulator. So for any developer, security researcher, anyone who's dealing with smart contract systems that involve governance, or even that don't involve governance. So I think that this tool actually solves a lot of issues around bugs in deployment scripts and bugs in governance proposals. What this framework allows you to do as a smart contract dev or engineer is very easily reason about the state that your protocol will be in post governance proposal or post deployment. It wraps everything up into the standard format that we're going to get into in this file. And then it allows you to, essentially integration test your system immediately post proposal, exactly as it's going to be done with the governance proposal, and or exactly how the system is going to look based on your deployment scripts. So I've seen a lot of projects where the deployment script is something that's usually overlooked because it's usually not in scope, so auditors don't look there. But I think there's been at least one example of $10 million going missing, or more, might have been 10 or $11 million going missing because the deployment script actually wasn't tested. And I don't want to name names, but I think that having that amount of money go missing is enough to warrant making tooling to make sure that you never have that kind of mistake again. And there's also been many, many cases of governance proposals not doing what their authors intended, and and then not being thoroughly integration tested, and a lot of money going missing as a result, or a lot of users being impacted as a result. So we built this framework at Solidity Labs to, it's completely open source. It's completely, completely free, always will be. And you can take a look at docs.soliditylabs.io. Looks like it's, okay. Yeah, so you can check out kind of how this works here. It allows you to like standardize your governance proposals, safely generate call data, and prevent bugs in your deployment scripts and your governance proposals. And so the call data that we're going to generate from this is going to be the exact same call data that's used on your system in the integration tests. So I'll go ahead and drop this in the, okay, I guess I can't comment here. That's fine. I just encourage everyone to take a look because that'll kind of get you familiar with how we structured this code base. So we have the description here. This is MIP M17, so it's a proposal on Moonbeam, so it follows that convention. We have a README file here of the proposal description, so that's great. And so now we jump into the standard functions that are expected of a forged proposal simulator gov proposal or deployment script. The first thing we have here is the deploy function. So the deploy function takes in this addresses object, and this addresses object allows us to keep track of the addresses that we changed during a governance proposal or a deployment script. And so we first go ahead and we deploy the MERC20 delegate fixer. So we have to deploy this contract using this deploy code function because MIP M17 and Forged Proposal Simulator is on Solidity 0.8 and above. And this code, this MERC20 delegate fixer, is Solidity version 0.5.17. So we can't import that code here. So we have to use this deploy code, which is a Foundry built in that will allow you to deploy a contract just by passing, the contract file name and the contract name. Once we deploy the logic contract for the MERC20 delegate fixer, we add it to the address as MERC20 bad debt delegate fixer logic. And then we also deployed the MERC20 delegate MAD fixer. And we add that as MERC20 delegate fixer Nomad logic. It's also important to note that in addresses.sol, when we call add address, oh, that's interesting. So this isn't the current version of Forge Proposal Simulator. This is a few commits behind the main branch, but you should not be able to add an address that is 0. That is the source of potential bugs. So we may have just found an issue here, but I need to check the current implementation, because it should not allow you to add an address that's 0, because then maybe this could have failed and then it silently, silently just failed and added an address that was 0. And I've also seen previously in using this framework that it's a source of potential bugs to have address zeros, anywhere. So instead of having, being reliant on external security researchers to find issues like address 0, the Forge Proposal Simulator framework actually, does a bunch of null checks for you. So if you try to get an address that doesn't exist, or if you add an address that, already, and it's address 0, or you're adding an address with a name that's already in use, that's a source of potential issues. So we want to handle that all for the user, for the developer, so that they make less mistakes and that they find them faster. So we've covered the deploy function. We've deployed 2 contracts, 2 logic contracts, 2 delegate contracts. Now it's time to go on to the build phase of the proposal. So here we are going to push the action for the Frax market to upgrade the implementation to the bad debt delegate fixer logic contract. So we set the implementation. We call set implementation on the Moonwell mfrax delegator. I think this is false because this is saying whether or not we want to do any sort of external call as we do this, and then or any sort of upgrade, and then do we want to pass any call data? And so we say no call data and no bytes. Okay, and then we have the description here. We're going to upgrade the delegate contract for mfrax to the delegate fixer. We need to do the same with the mxc dot token. We call set implementation with the same MERC20 delegate fixer address. We're not going to be making any calls, and there's no bytes to pass. Pretty simple so far. Now we need to go and we need to fix all of the users. So users that have bad debt that they're never going to repay, we need to load up all those users from the JSON file. And so we go read those in, we parse the JSON, we decode them. It's just a struct with address as a single field. And it's an array of these structs. So that's what we're looking for. We get the mfrax address. We iterate over all of the debtors that have bad debt. And we say, if you have a non-zero borrow balance, then we're going to go ahead and we're going to fix that user. So we're going to seize their collateral tokens if they exist in the governance proposal. And the governance proposal will also zero out their borrow balance and add that onto the bad debt if the user has bad debt. So one potential issue would be if there were users in the JSON file that don't have any bad debt and are being unjustly liquidated, because governance is trusted. And in the M token itself, we don't make any calls to the comptroller to determine the overall health of an account. So therefore, a user that is healthy and has a borrow balance could still be liquidated. But we wanted to just kind of simplify things and not have unnecessary or unneeded external calls. So we don't have that check. And as is, the governance proposal execution is around 6 million gas, give or take. It's over 6 million gas for sure. So the transaction limit on Moonbeam for gas is 13 million. So we can't go above that. So we wanted to make this as like minimal as possible because there's a lot of actions that have to happen here. Okay, so we call fix user, and then we have a description for that user of, liquidate bad mfrax debt for user, and then we turn the hex to a string of the address. So we pretty print it so that it's human readable, so that when we have when we run the deployment script, everything goes according to plan. Okay, so we've fixed all of the mfrax users. Now we need to fix the mxc.users. So we go ahead and we parse that, go decode it, and now we iterate over all of these users. We don't need to use unchecked because, this is all just running locally for call data generation. So I was going to say because it's an older version of Solidity and they just did that for us, but this is Solidity 0.8.9. We iterate over all the users for mxc.debtors. We make sure they have a borrow balance greater than 0. We call fix user.
Hey Elliot, just to jump in real quick. So I gotta bounce off. But we have Voss here who will be hosting for the rest of this. So
awesome.
Yep. Thank you all.
Jim.
Talk soon.
Bye, Pat.
Voss.
Sorry for the interruption. Okay. You can continue.
Oh, all good. See you, Patrick. Okay, so fix user. So we have the fix user function, so it's the same thing that we did up here. We have the reallocation multisig and the user address. So we do the same thing for mxc.debtors, where we go ahead and we go ahead and fix the users for all the users that have a borrow balance stored that is non-zero, and we liquidate the bad mxc.debt for the user. Now, once that's done, we need to do the final 3 actions, which are upgrading the Nomad USDC, ETH, and BTC addresses. So, that's what we're doing here. So we call set implementation on the MUSDC, Nomad USDC M token with the new MERC20 delegate fixer Nomad logic contract address. Again, we're not going to make any external calls in the upgrade. We're not going to pass any call data. And then we say, okay, hey, we're updating the MUSDC.mad M token to the new MERC20 delegate MAD fixer. We're sweeping all of the underlying MAD assets to the reallocation multisig for the MUSDC contract. And then we do the same thing for BTC and ETH MAD M tokens. So we set the implementation to the new address for the Nomad ETH token. And then we go through that. We sweep all the tokens. We have the set implementation function here again for BTC, and we go through that and we set the MERC20 delegate MAD fixer address. And then we go ahead and sweep all of the MWBTC, we sweep all of the ETH, and we sweep all of the USDC. So that about concludes it for the governance proposal. Then we do a simulation run here, and then we have a whole bunch of validations that, that all the users now post proposal, they have no debt, but they also have no balance for both Frax and the MXC dot markets. So we can check that there. we make sure that the balance of the reallocation multisig increased correctly. We make sure the cache of all of the Nomad markets has been moved to 0. Make sure, that the reallocation multisig amounts are correct. So that is the and the validate function. I think that I really don't think it needs to be reviewed, but and then we also have, so now let's go take a look at how we use Forge Proposal Simulator to leverage this governance proposal. So we go ahead and we have this integration test that inherits from post-proposal check. So post-proposal check inherits the MIP M17. It creates a new version of this contract. Then for the test suite, it goes ahead and makes a new test suite. So we can go ahead and look at what the test suite looks like. So the test suite is essentially a runner that will run the your proposals. So we go ahead, we deploy the proposal here. We make a new test suite and we pass in the proposal address as part of the array. And then we get the addresses from that test suite because it will go ahead and instantiate a new addresses object, and we use addresses path. And so that is addresses.json, which is exactly what we expect it to be. So we go ahead then and inherit the post-proposal check in this contract. And we have this setup function that's public and it's virtual. And we're going to see why it's virtual in a second. What we then do is we have some constants here. And I'm going to leave this up to the Hawks to review. But there's we etch on bytecode to any sort of Polkadot or Moonbeam specific precompile for ERC20 tokens, as that will fail in all Foundry integration tests. So we have to mock out some of these tokens, but that really shouldn't change behavior of things. We go ahead and deal some balance. And in our setup function, we cache a bunch of values from the system before we run the governance proposal, and then we call setup after we run the gov proposal. And then there's a whole bunch of validations to make sure that it does what we want it to do. You can't initialize the logic contracts. The cache is correct. The MAD markets cease functioning for across the whole place. We make sure that XC dot is set up correctly. There's a whole bunch of checks that we do, and feel free to review this entire file and make sure we cover all the paths, and that's great. But yeah, now I think we should go on to the formal specifications if there's no questions so far. Okay. What is the reallocation multisig? So the reallocation multisig is an address that was decided on by the community. So let's go ahead and try to find this. There's a request for proposal here. Yeah. So there's, as defined in the original RFP, there's a community-owned multisig that will take custody of the collateral of the underlying Nomad collateral, and that will be used in liquidation. So I think that's yeah, it's just, you can assume it's just a trusted third party. So let's go here. So let's go back here now. Any other questions? Feel free to just read them and let me know. Let's go ahead and look at the formal specifications now. We can also
we have another question. Here is he says, also, can you explain what is the Nomad and Mad stuffs?
The Nomad and what is the Nomad and Mad stuffs? I think so Nomad was a bridge that was hacked. And so we use .mad as a naming convention to denote a Nomad asset. And the beginning of the stream, we also go into further detail of the entire situation. So if you need to, feel free to rewatch. And also the README also contains further context on this. Okay, so let's go to the let's go to the share price specification. So the share price specification, here we want to make sure, beyond a shadow of a doubt, that none of these new functions that we have introduced are going to have any issues. So before we continue here, it's important to state some of the assumptions that have been made. So we do assume that all calls to accrue interest, they return 0. They return no error. So we've essentially mocked out these calls in the Certora prover. So this is a potential source of acuity where you think that a rule passes, but in fact it does not. So this is just something to keep in mind as you're reviewing these specifications. But yeah, and then we have essentially some constant values here. And so it's worth just 1 is just 1 to the E18. U at max is the solidity U at max. So we want to know that fixing a user increases bad debt. Like for all states the contract could be in, there is no state where you fix a user and the bad debt does not increase. So we first get the user borrow snapshot, we get their bad debt. I guess we don't really use these variables, so we could technically remove them and make it simpler. So we get the current user bad debt, or maybe we couldn't. I think it'll be fine to actually remove this. There was some other logic that was removed, I think, in this specification. So we get the bad debt of the total system. We fix the user. We get the bad debt after, and we make sure that the bad debt after is greater than the bad debt before. And we have seen that this rule does in fact pass, but feel free to run the rules yourself with these 2 commands here, so that you can see that the latest runs. And there's also a link to this run of the share price spec in the docs. So we fix the user. We make sure that the bad debt increases for all all the ways that for all the states the contract could be in. Then we say we're going to fix the user with 0 borrow balance. We're going to fix the user and we're going to make sure that their borrow balance is 0 and their balance is 0. So we start off here, the user and liquidator, starting user balance and the starting liquidator balance. We assert that the ending user balance is 0 and that the starting liquidator balance plus this is equal to, or the current liquidator balance is equal to the starting user balance of this and plus the starting liquidator balance. So this is just saying, this is like a more advanced fuzz test that actually gives us guarantees about the properties of the system, that anytime you perform a liquidation, the user balance goes to the the user balance goes to the liquidator. And I guess there's one more check that we could potentially add here, which is that the liquidator assert that the liquidator is not equal to the user, because if the liquidator is equal to the user, the call to fix user will fail. So we could just go ahead and add that just to be 1000% sure. I think that's overkill at this point. Now we want to make sure that the fixing the user does not change the share price. So we get the exchange rate current. What this does is this will call accrue interest. It's a mutative function. It's not a view function. So it changes the state, accrues the interest, gets the starting share price. We call fix user, and we make sure that the exchange rate after we fix the user is the same exchange rate as we had before fixing the user. Then we have, repay bad debt decreases bad debt. So essentially get the current bad debt amount, and then we repay the bad debt with cash, and then we make sure that the balance of the sender, of the message sender, decreased by the repay amount. We make sure that the balance of the fixer contract increased by the repay amount, and we make sure that the bad debt decremented by the repay amount. So we assert all these state transitions are true. And now we can move on to the next one, which is just bad debt rules in general. So here we want to make sure that okay, so this is a fun one. So we get the starting share price. So this calls accrue interest. So we get the current exchange rate. We make sure that the message sender is not equal to the fixer contract itself, because this actually caused issues. And this was how Satora caught a bug in the Kashi lending market contracts, because there was a way for the message sender to be the contract itself in that system. Here, there is no way for the message sender to be the fixer contract itself. So yeah, so we're not going to, okay, I gotta jump here in 10 minutes. So we're gonna rule this out to prevent over approximation of the possible states that the system could be in, or who the sender could be. Get the exchange rate, bad debt, and the balance. We call one of these three functions, and then we say, okay, we assert that the starting cash plus the starting bad debt, if these two values are less than the UNT max, which means that we're not going to have any sort of overflow, then we know that this implies that the exchange rate stayed the same. Because if the bad debt plus the cash, the starting underlying balance of the M token, is greater than UNT256 max, then it's just going to say, hey, we can't reason about the state of the system. So then we have, if ending bad debt is greater than starting bad debt, it implies that we called the fix user function. And then if the starting bad debt is greater than the ending bad debt, which means that we have repaid debt, it implies that we called either repay bad debt with cash or repay bad debt with reserves. We have some more rules here. I really like this symmetry function. So, or this rule around repaying bad debt is essentially symmetric. Like each value in the system moves 1-to-1 in just different directions. So we make sure message sender is not fixer, get the total borrows before, get the bad debt and the total reserves, and then just say, okay, get those values after. If the total borrows after is not equal to the total borrows before, it implies that the total borrows before minus the total borrows after is equal to the total bad debt after minus the total bad debt before. So this is just saying if our borrows changed at all, then the difference in the borrow value should equal the difference in the bad debt value. And And so that means that we call the fix user function. If we're here, then we say if the total reserves before is not equal to the total reserves after, that's going to go ahead and imply that if the total reserves and total change, it implies that the bad debt changed, and that those two values changed by the exact same amount in different directions. Actually, no, in the same direction. Whereas the total borrows are going to change, and total bad debt, those values, the total borrows decreases and the total bad debt increases. Here, the total reserves decreases, and so does the bad debt. So the bad debt moves 1-to-1 exactly with the reserves in the case that repaid bad debt with reserves is called. So I think I'm going to stop there. There's actually more stuff in the README to do that I haven't covered here. So feel free to run through the Slither activities where you print out the variable order. I think another thing to look for is, did we somehow, is the diff that we provided correct? Because we're changing a very little amount of code here, but assumptions are very bad. So we encourage you to take a look at the ad fixer. We encourage you to take a look at the MERC20 delegate contract and diff that with the live contract for mfrax and mxc to make sure that nothing has changed there. And yeah, I think that's all from my side. Are there any other questions?
I think this was amazing. One of the main problems we face as auditors is that we spend that much time trying to understand how the code base works, and having you here explaining function by function and how all the code base works is going to be a huge help for all the auditors in this competition. So I think that synchronously we don't have more questions. However, remember that you can always reach us on Discord or any other social media and ask any question about this competition, and we will be glad to provide more assistance. As Elliot said, please remind to check more the README and try to rewatch this live stream to understand better how the code base works. But I have to say, Elliot, this was amazing. I enjoyed a lot watching how you explain how the code base works. I would like to participate myself. Unfortunately, I cannot because I work in Cyfrin, so it's prohibited to me. But I would love to do so because I really like how the code base how the code base you explain works. So thank you very much, then.
Awesome. Thank you so much, guys. Happy bug hunting. If there are issues, yeah, go get them.
Yeah, we help our auditors find a lot of interesting security vulnerabilities for this contest, and we hope it's going to be helpful for Moonwell as well. So thank you very much. And again, if you have any questions, please let us know asynchronously on Discord or any other social media. Thank you very much again, Elliot. And if that's okay for you, let's close this stream, right?
Awesome. Thank you so much, guys. Nice meeting you, Vasily.
Thank you very much. Bye-bye.
Bye.